Okay, so today we are looking at mechanical energy. So let's get right into it. So from previous lesson, right, we have these two forms of work energy principle, right? We said that, initially we discussed how net work is equal to change in kinetic energy. And then of course we said that net work is essentially work done by conservative force plus work done by non-conservative force. So this is from last lesson. And then we talked about how work done by conservative force is actually just a negative change in potential energy. Okay, and so by putting this all together, we end up with this kind of equation here that work done by non-conservative force is equal to change in kinetic energy plus a change in potential energy just by rearranging, right? Remember that triangle means change in, and that's the same thing as a final quantity minus initial quantity. And so really we can expand that a little bit more, right? And so that's what we will have a look at today. So we are first going to discuss situation where we ignore non-conservative forces. So these situations, only conservative forces are doing work on the system. Okay, so we're ignoring things like friction, air resistance, those kind of things. And if we do that, we actually arrive at a particularly simple and beautiful relation involving energy. So starting from this equation, if we say that, non-conservative work by non-conservative force equals 0, then we just get this thing here, change in kinetic energy plus change in potential energy equals to 0. And what that means then is we can expand that into this one. So change in kinetic energy again, right? So kinetic energy at 2 minus kinetic energy at 1, or final minus initial, plus final potential minus initial potential gives you 0 in total. So to make it a bit easier on us, we are going to define another quantity called E, right? So this E is going to be our total mechanical energy of our system. Okay, so total mechanical energy is defined as the sum of kinetic and potential. And so from there, we can come up with a useful and very, again, profound principle in physics that the total mechanical energy of a system is a conserved quantity. Again, that's only happens when we ignore things like friction and air resistance. So when non-conservative forces act, when only conservative forces act, so ignoring all non-conservative forces, the mechanical energy of a system is conserved. I'm using system here very loosely, and we will explore more what I mean by system in module 3. But essentially, think of a system as like an isolated box, right? So a box that, nothing can pass through, no matter or no energy can pass through. So within this system, if there are no non-conservative forces acting, so ignoring air resistance friction, then we can say that the mechanical energy is a conserved quantity. Why is it a conserved quantity? Because the change in, because from here, right? So we've seen that we can then just write that because change in PE plus change in KE equals 0. And we say that, PE and KE is just change in mechanical energy. So we can say that change in E equals 0. The change in mechanical energy of a system is equal to 0. And so if the change is 0, that means that the value has to remain constant. Again, with energy, I don't really care what the exact value is. The change is the more important part, right? And so in this kind of system, mechanical energy is a conserved quantity. So that's summed up right over by this statement over here, right? So that says that if only conservative forces do work, the total mechanical energy of a system neither increases nor decreases in any process. It stays constant. It is a conserved quantity. And so again, from there, we can rearrange the equation to say that, well, then that has to mean that the change in my potential energy has to be equal to negative change in kinetic energy, or you can put the negative the other way around. So change in kinetic energy has to mean an increase in kinetic energy has to mean a decrease in potential energy, and vice versa. Now, you would be somewhat familiar with this already because we have done questions like these, but now we're just kind of formalizing it, right? Anything else I have to mention here? Yeah, yeah, yeah. So with the things that we've got here, right? We did say that it only works when only conservative forces do work, and we can ignore non-conservative forces. But if you have an object that's moving slowly enough so that air resistance is small enough, and like there are no surfaces that things are like rough surfaces that things are sliding on each other, then we can reasonably make an approximation for the situation using this equation as well, right? So with this one, yeah, again, it's about compensation, right? If I increase potential, the kinetic has to decrease. If I increase kinetic, the potential energy has to decrease, and the total amount has to remain constant, right, over the whole journey. Now, this was a bit of a journey for us to get to, I guess, this equation. Now, a lot of people will just kind of show you this equation and then just be like, "Yep, accept it and move on." But I think it's a lot more fun if you kind of know where or how we get to this point in the first place, right? Because sometimes it is about the journey rather than the destination itself. And so now we can try to use this equation for different things. Okay. All right. Yeah, and oftentimes it's actually easier for us to use the conservation law, so conservation of energy, rather than kinematics equations or Newton's laws, because those ones are vector quantities and you need to keep track of direction, whereas energy is a scalar quantity, right? Which means that I can just add the numbers and it's fine. Yeah. Okay, let's do an example. So this is a simple example of the conservation of mechanical energy. Again, we are going to ignore air resistance. And so we have here a rock is allowed to fall due to Earth's gravity from height h, right? So some height here. We don't really know what the height is. Doesn't really matter. All right, doesn't concern us too much. Or actually, in the question, it does tell you the height. But yeah, some height above the ground. So if you think about it, right, if the rock starts at rest, all the initial energy is going to be potential energy because it's not moving, so there's no kinetic there. The only force acting on this, like as I let go of it, is going to be gravity, which we know is a conservative force. And we're ignoring air resistance. And so we can just apply our simple conservation of mechanical energy equation to the system. Okay. Uh, as the rock falls, the potential energy is going to decrease. So starting from here at this height, right? So you have this much potential, right? And then as it falls down, now the potential energy decreases, but the kinetic energy is going to increase, which makes sense, right? Because the rock is now speeding up towards the ground. Yeah. And the important thing to note is that if I sum or if I add up the potential energy with the kinetic energy here, the total is still the same. So if I start off at 100 here for potential energy, then if this is 50, the other one also has to be 50. So they have to be equal amount because when I add it up, they have to be equal to 100. And then at the bottom there, that also has to be equal to my starting point because mechanical energy cannot change in this kind of system under our assumptions. Okay. And so that's useful because now I can do some maths with it, right? Because I can go, well, the total mechanical energy at point 1 has to be equal to total mechanical energy in point 2. So at this point here, I know I can calculate my mechanical energy. At point here, I can then also calculate my mechanical energy. So let's give it a try. So as it says here, initial height of 3 meters, and it wants me to calculate the rock's velocity when it has fallen to 1 meter above the ground. So let's start off by, should I just add an extra page? Yeah, let's add an extra page. Why not? For the lols. Okay. So, starting height. So my, let's just apply the equation, right? So change in potential energy has to be equal to negative change in kinetic energy. So if I expand that, that tells me that my potential energy final, so mg, you know what, I'm gonna do this mg, I'm gonna factor out mg, and then I can have h final minus h initial is going to equal to half half m factored out, and then because this is minus changing kinetic, that's equivalent to vi squared minus vf squared. Right, so normally, if it's just delta ke, that's going to be half m times vf squared minus vi squared, but because I put a negative here, it works out so that it becomes initial minus final instead. You can just do the whole thing, see if it works out, but that's how the result kind of pretty much end up, right? So don't just take my word for it, actually try it out and see if it actually, works. All right. First thing you notice straight away probably is that there's m on both sides. So that means this m can cancel out with that m. So I don't actually need to know the mass of the rock, which is awesome. Then I know that my initial height is 3 meters and my final height is 1 meter. Okay, so let's plug that in. So now I have 9.8. My final height of 1 minus my initial height of 3 is going to equal to half times my initial velocity. The rock was initially at 0, so put 0 there. And then final is what I want to find. So this final here is not when it drops, but it's when it's at my 0.1, right? So at 1 meter. And so now I can just solve for this. So move the 2 over, so it becomes 2 times 9.8 times, well, 1 minus 3 just minus 2. And then the negative, put a negative in front. And then because this is a square, so I have to square root it, right? And that should give me equal to VF. And so VF is equal to, my calculator, 2 times 9.8 times 2, 6.26. So let's say 6.3. Right, about 6.3 meters per second. Right, so 6.26. Here you go. Yeah, so I think that's much easier than using kinematics equations to solve for it. Pretty straightforward, I reckon. But I do want you to try to confirm the result. So confirm that you can actually get this number with the kinematics equation. So work out what the acceleration, or the acceleration, the final height. So just plug into your kinematics equation, see if you get that velocity to spit out from the other end as well. It should give you the same result. The other thing I want to note is that oftentimes people are really, really, really horrible at keeping track of positives and negatives for this equation here, potential and kinetic energy. So I want you guys to be better, right? Be better than your textbook is a great example. Your textbook sucks at keeping track of positive and negatives for these kind of equations. So for you, I want you to try your best to make sure that you keep track of the positive and negative value, right? Yeah, keep track of what's my final height, what's my initial height, and then if you do it all correctly, the negatives should either cancel out or stay there, right? So don't just be like, oh, it's a negative number, just ignore it, right? So try not to do that, because that builds up bad habit, and that's how you make mistakes. So keep track of your positives and negatives properly. Okay, next one. I've got here roller coaster car. Yep. And I have here, assuming the height of the hill in figure 6.18 is 40 meters. Yep. And the roller coaster car starts from rest at the top. Calculate the speed of the roller coaster car at the bottom of the hill, and at what height will it have half the speed. Okay, so I have to work out the speed at this point right here, and then I have to work out at where is my speed going to be equal to half of whatever is going over here. Okay, cool. Right. Okay, so let's try it out. add a page. Again, for this one, for now, we are just going to assume no friction, just to make our life easier. And another thing to note also is that, again, for these ones, it's good to get into the habit of analyzing if there is actually other forces acting. But for this card here, I have force of gravity acting down, right? But there's actually another force, right? The force of normal force. Now, normal force is not a conservative force. It's still acting there. So how come we can use our special equation? Well, the reason why we can do that is because normal force, in this case, in this situation, is always acting perpendicular to my velocity. Right? So velocity is always going to be perpendicular to normal force because that's just how tracks and roller coasters work, right? Hopefully you're not like flying out of the track. So your velocity is always going to be parallel to the track, and your normal force is always going to be perpendicular to the track, right? And so that means then that this situation, right, the normal force actually does no work. F does no work, which means I can ignore it for my energy question because it's not doing any work, so it's not transferring any energy. And so for all intent and purposes, the only force that's doing any work in our case is the force of gravity. And so therefore only conservative forces is acting on the roller coaster because we're ignoring friction and air resistance. And so therefore I can apply my equation, right? Cool. So let's solve the problem. Also going to ignore the rotation of the wheels and all of that, and going to treat the roller coaster thing as a point particle because, again, it's too complex otherwise, right? So let's just treat it as a simple ball rolling down the ramp. But yeah, like in real life, it's going to be a bit more complicated than that. But it's all right. We're just doing physics. It's high school physics. Okay. Sorry, where was I? Yes. So MGH minus potential energy is going to equal to change in kinetic energy. So starting on from that equation, expanding it out, right? So again, going to do this mg, and I have minus in front here, so it's going to be initial height minus the final height is going to equal to change in kinetic energy, which is going to be equal to half m times Vf squared minus Vi squared. Now, it's important then that I actually go back and define my coordinates, right? Because if you remember, energy is all about relative, right? So I can start here to be 0 and here to be minus 40, or I can start here to be 0 and here to be plus 40, which I think is what I'm going to do. So I'm going to start 0 at the bottom, and then at the top is when it is 40 meters up. And so if I go that way, then I can say that I want my initial height to be 40, and then I want my final height to be 0, right? Because that's when it's at the bottom of the ramp. And so that's what I'm looking for, right? Yep, that is what I'm looking for. So let's just plug it in. Again, m's cancel out, so that's fine. So I have 9.8 times my initial height, which is 40, minus final height, which is 0, is equal to half times final velocity is what I'm looking for. And my initial velocity is 0 because I think it started from rest. Is that correct? Let's see, the roller coaster that starts from rest. Yep, so that's fine. So then solve this equation. I just have 2 times 9.8 times 40, because 40 minus 0 is 40, is equal to Vf squared. And so I have to take a square root of this. And so that should give me the answer of 2 times 9.8 times 40. Make sure you try it yourself as well, please. Don't just watch me do it. Make sure you do it. 28 meters per second. Okay, and so now I've found out that the velocity here is going to be 28 meters per second. Now, part 2, it asked me at what height will it be half the speed. So I'm looking for the height that is at 14. Right? So half of 28 is 14 meters per second. So now, so this is part 2 or part B. part B. Again, can use the same equation, right? Minus change in potential is equal to change in kinetic. But now I have a different goal, right? So I want my starting point to be 0, and my final point is going to be 14 meters per second. Okay, and I'm looking for the height. And so if I expand the equation, mg delta h, so hi minus hf, because of the negative, is equal to half times m vf squared minus vi squared. M's cancel out. My initial height is 40, and I don't know what my final height is, right? So I'm looking for my final height is equal to half times final is 14 squared minus 0 squared is my initial. So to solve for this, again, just simple rearrangement of equations, right? So I've got, okay, how should I do this? Move the h over to the other side. So hf is over here, and that's going to equal to, move the 2 over, so multiplied by 2, 9.8. Actually, I can't do that, can I? I'm going to need to, you know what, I'm just going to do it the long way. All right, 40 minus HF is equal to half times 14 squared divided by 9.8, right? That's all good so far, I think. And then I swap this quantity and the HF. So 40 minus half of 14 squared over 9.8 is equal to HF. HF therefore has to be equal to, listen to your calculator, half times, half times 14 squared divided by 9.8 gives me 30 meters. Okay, so what that tells me is the roller coaster traveled to about like here at this point. So at 30, it now has a speed of 14 meters per second. Okay, and then eventually it goes down to 28 at the bottom. And so, yeah, it's good to be able to calculate all of this stuff mathematically, right? So again, make sure you give it a try, please. But you also need to be able to explain it, right? So you initially have to be able to go, well, initially the car has only potential energy. As it goes down the hill, it loses that potential energy, it gains the kinetic energy. But again, the sum of the two remains constant because no non-conservative forces are working on that does any work in this situation. At the bottom of the hill, it has now reached its maximum kinetic energy, right? And so that's where it's max. And then as it climbs up the other side, the kinetic energy is now going to change back to potential. Right? So the roller coaster is going to slow down as it climbs up in height. And then the car will eventually, once again, comes to rest at the same height that it started from, right? So if it started from 40, then the car will come to rest when it goes to 40 over here as well, right? And then like, because it's an unstable, if it's an unstable point, then it's just kind of bounce back and forth that way forever, right? Cool. Yeah. Now, what happens then if this track goes slightly higher, right? So if this track is, it goes higher than 40 meters, so the track extends all the way here, then it's the same thing. The car is going to go up to the 40 point, and then it's going to slow down, come to a stop, and then fall backwards, and then go back to the initial point, and then come back, right? So it's going to kind of, again, bounce between the 2 points. However, if I have a track that is lower, so let's say instead of going up all the way to 40, it only goes to like 20 or only goes up to 30. Then what happens in a situation without any friction is that the car now has reached a maximum height, or has reached a height where it can't go any higher, but it still has some kinetic energy, right? And so the car is going to just keep moving at a constant speed forever until it reaches the height of 40, because it has some additional energy that it gained from the drop, right? Yeah, yeah, cool, 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 cool. Yeah, and so yeah, no matter how steep the hill is or what path I make, right? So the roller coaster could be this shape. It could also like it'll be not a great roller, or it'll be a really scary roller coaster, but like it could also drop like this. Oh, oops. It could also just drop like this, right? And that is completely fine. Like I don't care about the path because again, gravity being a conservative force is path independent, right? And so my potential energy purely depends on the height. It doesn't depend on the path at all, right? Which is awesome for these kind of questions, right? Yeah, cool. So what happens then if I actually add friction to the system? Have a think about that. Like, what actually happens if I add friction to this kind of system? Well, friction is going to slow down the car, right? Because what is friction? Friction is a non-conservative force, so it's going to do some work in order to oppose the motion here. And so, what work is it doing? Well, it's transferring the mechanical energy inside our system into heat, right? So, yeah. So as the roller coaster comes down, friction is gonna cause the air around it to heat up, and so energy is being lost and dissipated. And so what that results in is that the roller coaster won't be able to go as high. So without friction, the roller coaster will always be able to go back to the same height. But because of friction and air resistance and all those things, energy has been lost, and so now we won't be able to go back up to the same height, which is pretty much what we observe in everyday life, right? Like if I have a track like this and I have a ball rolling down, the ball doesn't like come to the same height as what I drop it, right? Because again, friction. So it might roll around for a bit, but eventually all the energy is dissipated as heat and the ball just comes to a stop. Okay. Uh, and so, yeah, friction does reduce the mechanical energy, which is consistent with what we have, right? Because we said that the work done by non-conservative force is equal to the change in mechanical energy of the system, right? Because, yeah, equal to change in kinetic plus potential, which is just mechanical. And so if there is work done by a non-conservative force, then the mechanical energy of my system will change, whether that be being added or being subtracted, right? In the case of friction, the work done by friction is always negative, which means the mechanical energy of my system is always being reduced. Okay. So hopefully that makes some sense there. Cool. So, also, quick note. This question you would not be able to solve using kinematics. So this question is only possible for you to solve using energy. Why? Because acceleration is not constant on this curved track, right? So if it was like a slope down, fine, I could probably like work out my constant acceleration down. But in this case, because the slope is curved, acceleration is not constant, and so my kinematics equations essentially gets thrown out the window. And so, yeah, it's not possible for me to solve it using kinematics. So energy again becomes really, really helpful in this situation. Cool. Let's move on. This one, more conceptual problem. So I have here two water slides, right, at the pool. They're shaped differently, but start at the same height. So I have, yeah, so start from certain height here, over here, and then it ends at the same height here as well. And the question says, two riders start from rest at the same time on different slides. Which rider, Paul or Corin, is traveling faster at the bottom? So who's going fastest at this point here? So at the finish line. And which rider makes it to the bottom first? Ignore friction and assume both slides have the same path length. That's an important part. Well, we know that, based on conservation of mechanical energy in a system, that I can ignore friction. So again, no non-conservative forces acting, right? So only purely conservative forces. That means that I can just apply my conservation of mechanical energy. And because of they started from the same height and they're going to the same point down there, I know that the kinetic energy at the bottom is going to be equivalent, and so both of them will be traveling at the same speed at the bottom. Okay, so regardless of like the path, they're all going to, because they go down the same height, they will finish with the same speed, which is cool, right? But the second part is what makes it interesting. Which rider makes it to the bottom first? I want you to lock in a guess. Okay, log in a guess now and see if you can logic your way through it. All right, ready? Okay, the answer is Corin. Corin will arrive first. Why? Because if you have a look, even though the path length is the same, right? It's the same path length, Corin has always been at the bottom of Paul, right? So always lower in height than Paul, right? What that means then is Corin always has higher kinetic energy. So kinetic energy of Corin is always going to be higher than Paul, even though at the bottom, right, they have the same kinetic energy. Along the path here, she has higher kinetic energy overall, which means that her speed is always higher. If your speed is always higher and the path length is the same, that means the time it takes for you to get to the bottom has to go down, right? And so the answer is Corin. She will be able to arrive at the bottom of the slide before Paul does. And so now you have a tool whenever you go to an amusement park or a water park like Wet and Wild, you can now do some calculations. Cool. Next slide. So back to some content. Besides the kinetic energy and potential energy of a mechanical system, right, we can also define other forms of energy. There are many other energies that you've probably heard of, especially in your junior years of science, right? Things like electrical energy, things like nuclear energy, things like thermal, chemical energy, etc., right? These other forms of energy can actually be classified into either kinetic or potential, right? So most different types of energy can be classified, yeah. So as it says here, right, it can be classified as either a kinetic energy or a potential energy, or sometimes it's both, right? Because yeah, sometimes things like electrical, right? Do they mean like the electrical current, or do they mean like the electric potential, right? So yeah, it depends on what they mean. Uh, but yeah, so the sum of the kinetic and potential is called mechanical energy. All of these other energy can pretty much be summed into potential and kinetic, albeit like yes, it doesn't always describe the macroscopic picture. Sometimes it describes the microscopic picture. So for example, things like thermal energy, right? So you probably have heard of thermal energy before over here, associated with like temperature and all of that. But with thermal energy, you're actually looking at the kinetic energy of the average kinetic energy of the particles in, like, let's say some substance, right? So if I say like this water bottle, the water inside has a temperature of 20 degrees, that means that it has a certain amount of average kinetic energy, right? So the particles are moving around a certain speed. And then if I heat it up, the particles are moving faster on average, and so it has higher temperature, so therefore higher thermal energy, right? And so really, yeah, again, like most energies, I can boil it down to either being kinetic or potential. And so that's what we concern ourselves with a lot for our course, right? Kinetic and potential energy. Another example, things like chemical potential energy, so food, like energy stored in like food or like petrol and things like that. Those are considered potential because essentially, if you think about it, like chemical bonds, like food and petrol, like where does the energy come from? It comes from chemical bonds, right? That's where the energy comes from. And chemical bonds, if you boil it down, essentially it's just molecules being trapped inside an electric potential of another molecule, right? That's all it is. And we'll look at this more when we look at quantum mechanics. But essentially, yeah, you have electrons being trapped inside the electric potential field of the nucleus. And so with that, we can essentially say that chemical energy is a type of potential energy, right? So what I'm trying to say is all of chemistry, the foundation of it is just physics. Um, and one of the things we say is that energy can be transformed, right? So like it can change from one form to another. Again, energy is just a way for us to keep account of things. So like for example, if I have water at the top of a waterfall or a dam, like we say it has some potential energy, and then that can be transformed to kinetic as it falls down. Uh, and at the base of them, maybe you have like a turbine blade to convert it into, or to transform it into, to transform all the kinetic energy into electrical energy and all those stuff, right? So, yeah, energy, like it's useful for us to have described in different forms, but really, like it's all the same. It's all just potential and kinetic, really. Um, Cool. And yeah, just remember that whenever energy is transferred from one object to another, work is done, right? So, for example, if I have energy transferred from the waterfall into a water turbine, then the work is being done by the water that's falling into the turbine. Cool. Okay, so then we actually come to one of the greatest result of physics, right? The result is, you know, whenever energy is transferred or transformed, we find that actually no energy is gained or lost in the process. Right? The total energy is neither increased nor decreased in any process. Energy can be transformed from one form to another and transferred from one object to another, but the total amount remains constant. Right? This applies to also non-conservative forces. So like we have seen that yes, it applies for conservative forces, right, which is potential and kinetic energy. Fine, that makes sense. But it turns out this law of conservation of energy extends even further, right? It's not just about the conservative forces, it's about all kind of forces, right? So all energies are conserved. As long as you can keep track and keep account of them, all energy is going to be conserved. And this is called the law of conservation of energy, right? It's probably one of the most important principles in physics, right? Uh, and the reason why I say that is because even though things like, like we've done Newton's laws, right? Newton's law seems pretty fundamental, but actually Newton's law, we find it actually fails when we look at subatomic particles, right? So when things are too small or when things are too large, Newton's law actually fails to apply. But the law of conservation of energy is so fundamental that it's been found to hold in every single experimental situation that we have tested so far. Right, so we haven't been able to break this law of conservation of energy yet. And I don't know what that tells us about energy, right? Because initially I did tell you that energy is a mathematical quantity we use to keep track of things, but somehow that thing is such a fundamental part of the universe that this law of conservation of energy holds in all situations so far that we have seen. Right. So pretty interesting. Yeah, something to ponder about. Okay. And it actually took us quite a while to discover the conservation of energy. Like, took us like this kind of law of conservation of energy wasn't well formulated until the early mid 1900s, right? So early mid 19, oh sorry, not 1900, 1800s. So the early mid 19th century. So yeah, 1800s. And the reason is because we have things that dissipate forces, like, sorry, we have dissipated forces like friction, right? So without friction, yeah, I'm sure we would have come up with conservation of energy way before, right? Because if I let the ball drop and it goes back up to the same height, yes, like, oh yeah, energy is conserved, duh. But because every time I let the ball bounce, it actually doesn't go up to the same height, like some of the energy is lost, and we couldn't quantify that, right? And so we actually didn't know that energy was conserved. Like, it might seem obvious to us now, but people back in the, like, for people back in the days, they didn't know that, right? And they weren't sure that, yeah, is energy a conserved quantity or not? But then turns out it is, right? um and it took, the reason why it was, started to be formulated in the 1800s, right, during the mid 19th century, is because that's when the Industrial Revolution started happening, right? Before the Industrial Revolution, we didn't know how to like mathematically describe heat, right? Because how do you describe something like releasing heat, right? But once people start thinking about industrial revolution, steam engines, like engines become the really important things, right? So how do I use the coal to make it do work in order to transfer something from one location to another? And so that was when the whole thing about thermodynamics starts to be developed. And then people could eventually quantify heat, and then heat, because heat is essentially just a transfer of thermal energy, right? Then we can actually now take into account, like, the heat loss in the process, which means that we can actually work out that, yeah, essentially energy is conserved, right? I have kinetic energy, I have work, I have potential energy, and I have heat, right? And so with all of that, when I add it all up, I actually work out that the number stays constant. Okay, so in any process, which is pretty cool. All right. Cool. Anything else I have to talk about here? I think that's fine. Actually, I do want to talk a bit about the roller coaster. If the roller coaster car is subject to frictional force, so like imagine back to this situation over here. Now, in this situation before, we ignored friction, but if we actually added friction to the problem, what would it actually look like? Well, if friction was part of it, then the initial total energy will be equal to the kinetic plus the potential of the car at any point, plus the amount of thermal energy being produced, right? So it will be, yeah, which is, so total work, right? So sorry, let me write it down properly. Total energy, right, of the car is going to equal to the kinetic energy of the car at some point, let's call it point one, plus the potential energy at that point, right, plus the thermal energy, so the heat being produced. So thermal energy, how do I normally thermal energy is defined, is like, it's Q, so I'll just use Q, plus the thermal energy that's produced in the process, right? And that part there is just the work done by friction and air resistance. So work done by friction and air resistance and all of that. And so I can mathematically kind of describe it, I guess. I could say that, well, the work done by non-conservative forces, starting from my work energy relation, right, is equal to the change in kinetic energy plus the change in potential energy. And then from there, I can go, well, this work done by non-conservative force is literally just work done by my frictional force. So minus force times the path length, right, is going to equal to, well, change in kinetic energy is K1 minus K2 plus P1 minus P2, right? That's what changing means. And so I can then work out that, well, my potential, let's see, how should I, what is that? My kinetic energy plus my potential energy at any point is going to equal to my kinetic energy plus potential energy at any other point, minus my friction force, like work done by friction, right? And so that's what I mean by energy is no longer the same, right? Because initially I have this, but now this is equal to this plus this additional term over here, right? So total energy essentially has gone down. Where does it go? It goes in as heat. If you don't fully understand that, that's okay. But I want you to have some kind, like, if you don't understand the mathematical part of it, that's all right. I just want you to have a good conceptual understanding of it. Okay. All right. Back to my slide. So whenever you're solving any problem with regards to energy, again, make sure you initially draw a picture, right? A picture is important so you can understand what's going on. Look at the system for which you apply conservation. So like what object or what forces are acting on it. So analyze the situation first, like pause, take a deep breath, look at what's going on. Ask yourself what quantity you're looking for. So are you looking at the initial point? Are you looking at the final point? Like, or are you looking at some points in between? Choose your initial and final points and then go from there. If the object under investigation changes its height during the problem, then choose a reference frame. So important to choose like where's your 0 point and stick to that, right? Normally it's convenient to have y equals 0 as the ground level. Yeah, and from there you can go from there. And then think about, is mechanical energy conserved? Is there friction, right? Or are we ignoring friction? is there other non-conservative forces that are actually doing work, right? So like if it's normal force actually doing the work, right? Or is it like perpendicular, right? Have a think about it. And then just apply the law of conservation of energy. So if friction or other non-conservative forces are present, then you need to add the additional non-conservative force, work done by non-conservative force term. And then, yeah, if you have like for constant friction force over distance, that's just equal to that because work is just force times distance, right? Yeah. For other non-conservative forces, use your intuition for the sign. Is the total mechanical energy increasing or decreasing in the process? So have a think, right? If the total mechanical energy is increasing, then your work done can be positive. If the total mechanical energy is decreasing, then the work done is going to be negative. And then use the equation to solve the problem. Like, but that's the general steps that you should probably follow. Okay, last slide. Let's try out this problem. So Phil pushes a textbook across a table towards Ranji, but it falls off the edge of the table. Consider motion in the vertical direction only and ignore air resistance. Great. So that means I have a purely conservative force situation, right? So no non-conservative forces. And then calculate the speed at which the book hits the floor if the table is 75 centimeters high. So let's draw it out. So I've got book here, pushed off, and an object falling down. This thing here, 75 centimeters. Anything else I'll talk about here? That's it. So I want a, yep. So I can essentially just apply my equation, right? So change in potential is equal to change in kinetic. Again, no non-conservative forces here because ignoring air resistance. mg hi minus hf because of negative. That's why it's not f minus I. That's why it's I minus f is equal to half m v f squared minus vi squared. Oh, be careful with this one, by the way. It is not half mvf minus vi squared, right? This is not the same. Not the same. Mathematically, not the same. So do not do that. Cool. Where was I? Yes. So let's say that my 0 point is down here. That means that my initial point is 75 centimeters up. So masses cancel out, right? 9.8. Whoops. All right, follow the process. Right, people follow the process. Process. Oh gosh, I skipped so many. Where am I now? Draw a picture. Tick. Determine the system. Yep, I'm looking at the book. Choose my initial and final. I think I've chosen it, right? So my initial point is my starting, yep, and the final, great. And then I have to determine my frame of reference and then think about my equation, right? So frame of reference wise, 0 down here, 75 on top. My initial, right? Again, 75. My final, 0 is equal to half times VF. So my final is what I'm looking for. And then VI is 0. And then if I solve my equation, I get that VF is equal to 2 times 9.8 times not 75 because I almost made the mistake. Because I want to be in SI unit. So it has to be 0.75 meters. There you go. 0.75 meters. 0.75 meters. There we go. And then take a square root of that. So that's now going to be equal to square root of 2 times 9.8 times 0.75. 3.8 meters per second. Or 3.834 blah 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 meters per second. And so that's how you would do it. Make sure you don't make the same mistakes I did, right? So make sure you convert everything to its SI unit to solve the problem. But yeah, that's mechanical energy, and we will be using this to solve a bunch of other problems. See you next time.